Alright, so I'm doing this video to talk a little bit about a refreshment on how to find the average rate of change of a function. Um, and for this particular problem, it's talking about this boulder, and this boulder is modeled by this equation. Hopefully, right, you either drew a sketch of how this function looks like, or you could use a handy dandy Desmos to help you make a model of it first, right? And then from that model, you want to determine what is the average rate of change over its entire fall. What does the entire fall look like, right, in the model that you're looking at? You're going to decide where its starting point is and where its ending point is. That's what it means by the entire fall. Once you have those two coordinate points, then you'll be able to calculate the average rate of change. So here's the video support. All right, so how we calculate the average rate of change, what you want to do is you want to go back to your resources. So where I'm at right now, I'm on the Chapter 7 Big Ideas packet. I'm on page 6. That's where it talks about finding average rates of change. Again, a huge big idea is that the average rate of change is you're calculating the slope of the secant line that connects any 2 points on the graph, right? But you don't really have to know much right now yet about like secant line, what it means, but basically the average rate of change slope formula is this one, the one that you all know very well. It's y2 minus y1 all over x2 minus x1. Now what I like about this right here is it gives us two examples, one with a table. See example 1, it gives us a table example. Notice how you had to label your point x1, y1, x2, y2, and from there you utilize the formula that was given to you, plug in, and do your calculations. This one was feet per second. That's why we have our units as feet per second. Now, if we look back at the problem that we were given, we don't have a table though, right? What we have instead is a function. Now, if you want to create a table for this, you can and utilize that, right? But I'm going to move down more, right? Because there's two examples here. So maybe the other example will help me out. So this is if I have a table, cool, I could find the average rate of change given the table. This in particular was between 3 and 6. So that's why we had 3. And then we had 6. And then we had to look for 3, you get 70, 3 comma 70. For 6, you get 297. That's where that number comes from, as a heads up. But again, this is if I'm given a table. Let's scroll down to example 2, where I'm given a function. Now look at this. This is the type of function we did in class. In this example, it says a car travels d of t equals 10 t squared feet in the first t seconds. So that means this right here represents feet traveled, and t represents seconds in this particular problem. After it starts moving, calculate the average velocity, or remember y'all, average velocity is the same thing as average rate of change. All right, so it's very the same. But this one's telling us between t equals 1 and t equals 2. Now what we had to do is, because it's the same between t equals 1 and t equals 2, I took the 1. First step is I took the 1 and I plugged it into my function. See how I'm plugging in 1 for t? 1 squared is 1, so 10 times 1 is 10. So then I get my first coordinate as 1 comma 10. Then I moved on and now it says between t equals 1 and t equals 2. So then I take 2, I plug it into my function to get my output. So 2 squared is 4. 10 times 4 is 40. So that's how I got 2 comma 40. Once you have your two coordinates, once you have those two coordinates, right, you label your points. Super important. And then you could go ahead and plug it into the rate of change formula, which is this one right here. Well, I don't know why this is kind of switched. This should kind of go before. Let me just fix that right now. That's interesting. This should go 4, right? Before. The formula needs to go first. You've got to know what you're doing first, right? What are you plugging into? Once you got your 2 points and you've labeled them, you're going to plug them into the slope formula. Y2 minus y1 all over x2 minus x1. And then you do your calculation. And for this particular problem, we get 30 feet per second. Now the question is for this problem right here, right? Once you're looking back at your problem, you're going to utilize this function now. You have a different function. This is modeling a boulder that's falling. Um, but it's cool because H represents feet, just like that car example. And then T is going to represent function, seconds, time in seconds, just like that car. It's asking us to calculate the average rate of change over its entire fall. So what you're going to be doing is you're going to be choosing what are the 2 points that represent the boulder's entire fall. Once you have those 2 points, then you're going to plug it into the slope formula and from there average rate of change. So I'm going to be interested in seeing how you all choose those 2 points. Again, you want to support your answer using a Desmos graph. You want to interpret what does the graph tell you about where the boulder starts, where it ends, how are you getting your 2 points. So that's my video help. Good luck, everybody.